Good morning students. Today we are going to discuss about the data encryption standards, that is DES algorithm. So these are the objectives of the DES. So to review the short history of DES, to define the basic structure of DES, to describe the details of the building of elements of DES, to describe the round keys or to generate the process to analyze DES. Coming to the introduction of the DES, so data encryption standard is a symmetric key algorithm which was published by the National Institute of Standards and Technology. So this was the one of the best algorithm for a longer period of time. So this was developed in the 1970s only. So we are going to discuss about the how it is going to work. So next topic is history and the overview of it. So in 1973, NIST published a request for the proposal for the symmetric key crypto systems. So a proposal for the IBM, a modification of the project called Lucifer, was accepted as the DES. So DES was published in the Federal Register in March 1975 as a draft of Federal Information Processing Standards. So coming to the overview of the DES block cipher. So we can see here we in this particular DES we are going to use the bit size as 64 bit and the key size is of 56 bit key, and when we are going to encrypt our plain text with the algorithm, and we are going to get the 64 bit as a ciphertext. And in the reverse, whenever we take the ciphertext, we are going to apply the same key, 56 bit key, and we are going to achieve the plain text at the decryption end. Coming to the structure of the DES. So initially the structure contains two permutations or two P boxes, that is initial permutations and the final permutation, and the number of rounds that you are going to bear in the DES algorithm is 16 rounds. So let us see how the initial, next we are going to discuss about the how the structure will be there, what are the internal rounds and what are the round functions that are going to be there in the this DES. So coming to the structure of DES, so general structure is we are going to take the 64-bit plain text, then we are going to give into the initial permutation. So this initial permutation is the already predefined initial permutations. Permutation is nothing but the transposition of the bits are going to take place. So we are going to change the positions of the bits that we are going to there. So that is initial permutation. Then those particular after the outcome from the initial permutation is given is as a round 1. So in this round 1 function, we are going to have the expansion function S boxes and so on, and we are going to XOR with the bit key of 48 bit. So initially we had 64 bit of key which was decreased or compressed to 56 bit key. Then it was furtherly at the each round, that is for 16 rounds we are going to give 48 bit key, and then we have the final permutation and we are going to get 64 bit key ciphertext. So the process of the structure of the DES is, so initially we are going to take the 64-bit key plain text. Simultaneously we are going to also take the 64-bit key. So the 64-bit plain text will be given to the initial permutation, and the 64-bit key is given to the permuted choice 1. So this permuted choice 1 is also predefined table where you have the similar to the permutations only, where you are going to transpose the values. That is, we are going to place the values. That is, the 64 bit is being placed to the numbers that are there in the, or we are going to transpose the values in the required. For example, you can take like the initial permutation values are like this. So we are going to get, suppose if I have 1 to 64 as the plain text. So my 58th bit comes for the first value. First value becomes the 58th bit, and the second position becomes the 60th bit. 60th bit. The third position will be 62nd bit. So like that we are going to transpose our values of 64 bit in till the whatever the numbers that are there, all those numbers we are going to replace. Similarly, in the permuted choice 1 also, the 64 bit is being compressed to 56 bit. So here there is a certain logic, that is, you can observe that the 8 table, that is, the multiples of 8 are missing. So the multiple of 8 are being removed, and other all, that is, the 8 bits are removed, and we are compressing the 64 bit to 56 bits. So this permuted choice 1 is again the 64 bits, that is, if at all we have 1 to 64 bits, these 1 to 64 bits, we are going to remove all the multiples of 8, and of 8 bits we are going to remove, and we are going to place the 57th bit in the first position, then first bit in the second position, third bit in the 10th position, 10th bit in the third position, our 19th bit in the fourth position, our 63rd bit in the fifth position. Like that we need to transpose the values in the required manner. Once you perform this, then we have the round 1 function. So before going the how the round function goes, so we need to know the key, how we are going to apply the 48 bit key. So once the permuted choice 1 bit key is being performed, we are going to get the 56 bit as the output. So this 56 bit key is again given to the left circular shift. So the left circular shift is depending upon the what round we are going to take. So if it is the round 1, then we are going to shift by 1. If it is round 2, then also we are going to shift by only round, only bit by 1. If it is also, then we have the 64th round, where we are also shifting by only 1 bit. But other than all these, we have the bit, 2 bits that we are going to shift left. You can observe over here. So we have taken the left circular shift. So in the left circular shift, so we are going to have, whenever you say left circular shift, so you have the bits like 0, 0, 0, 1, 0, 1, 1, 1. So when you are shifting for 1 bit, so this bit is transferred to the right side, and all other bits are shifted to the 1. So our left circular shift depends upon the round number. Suppose if it is a round 1, so we shift the bits by the only 1 bit. If it is of second, then also we shift by only 1. If it is of third round, then we shift by the 2 bits. So similarly, the 1 bit shifting is 1 for round 1, 2, 9 and 16 rounds. And all other rounds we are going to have the shifting of 2 bits. Then coming to, once you have done the left circular shift, so we are going to get the output as 56 bits. So these 56 bits are given to the permitted choice 2. So this permitted choice 2 values is similar to the transposition of the values. So we are going to replace the values to the required number. So since we are going to place those 56 values. So in this we are going to remove some 8 values, and we are going to compress our 56 bit values to the only 48 bit. So these 48 bits are this one. So the 14th bit is being given as the first bit value. The second bit value is nothing but the third bit in your plain text. 23rd bit in the text key will be the third bit value here. The 16th bit in the key becomes the fourth bit here. So like that we are going to transpose all these 48 bits, and this particular 48 bit value is given as the key for the round 1. So like that we are going to achieve the 48 bit key. So once you have got the 48 bit, so we are going to, so this is the structure for the 16 rounds. So once you have finished the left circular shift permitted choice 2, this round 1 is finished. So this process will continue for 16 rounds. So these 16 rounds, once the 16 rounds are finished, we are going to swap the 32 bit. So these 32 bits are being swapped. Then we are going to apply the inverse initial permutation. Then we get as a cipher text. So the initial and the final permutation steps are, so in the initial permutation, so the first value is given to 40 and the 58th bit is given to 1, and my second value or my 8th bit is 2. Second bit value becomes the 8th bit in the initial permutation. So similarly my 25th bit value is nothing but 64 bit in the plain text. So like that we are going to take in the similar way, we are going to have final permutation also. Here also we are going to replace the transpose the values. So my first bit becomes the 58th bit over here, and my 40th bit in the plain text becomes the first bit. So like that we are going to replace. So these are the initial and final permutation tables. So the initial and final permutations are straight P boxes that are inverse to each other, and they don't have any cryptography significance. So we use 16 rounds in the DES algorithm. So at the each round we are going to achieve a Feazell cipher, that is Feazell structure. If this Feazell structure is structure where we are going to divide the 64 bit into two parts. One is 32 bit left and the other one is 32 bit right. Then we are going to take the 32 bit right values and we are directly put into the left of these round 2 values, but the left values are again given to the round 1 function. So you can see here we are going to divide the left bits as well as the right bits. So the left bits are given and XORed to the directly, the right bits are given to the left bits, and these right bits are done the function is given to the round function. Then we are going to take the output value from that round function and XOR with the left 32 bit. And we are going to take those values as the next round function right bit values, and directly the right bit values becomes the left bit values. So here when you take the 32 bit, so we are going to do the expansion. So in the round function we have the expansion permutation. So here also we are going to transpose the values. So all the 32 bit is converted to 48 bit values. Then we XOR with the key values. So like we have seen in the previous slides. So we are going to take the left shift bits, that is the 48 bit values, that is 56 bit values. We have done the left shift, then we have done the contraction where we have got the 48 bit, that is the permuted choice 1 we have done, then we have done the left shift, then we have done the permuted choice 2, then we have got the 48 bit data. That 48 bit key is applied to the round function. So in this here XOR we are going to do the key as well as the output from the expansion and permutation step. So once you do XOR, then we going to give that output to the S boxes. So we are going to have 48 bit as the input, and we are going to achieve the 32 bit from the S boxes. That 32 bit again we are going to put into the permutation or P box, or we are going to say as a transposition of values, where we are going to replace by the related number transposition numbers, and that values then we are going to get output as 32. So from that values, from the output from the permutation, we are going to XOR directly the left bits, left 32 bits, and we are going to take it as a right bits for the next round. And similarly here also we are going to take the left bits. Once the left circular shift is finished, we are going to take directly those bits as the left side for the next key. Here also for the right side, once the left shift is finished, directly we are going to take the next bits for the key. So coming to the DES function, so in the round function this becomes the heart of the DES function, and how this particular DES function will work is we are going to take 48 bit key to the rightmost 32 bit will produce the output. So 32 bit we are going to take the rightmost bits, then we are going to put that 32 bit data into the expansion P box, where 32 bit is being transposed to 48 bit. Okay. Then we are going to XOR with the key bits. 48 bits is XOR with 48 bits of key. Then we get output as 48 bit. Then these 48 bits are given to S boxes, and this from S boxes we going to get as 32 bit output. From 32 bit directly we are going to place again to the P box or permutation boxes, and we are going to again do the transpose. Then we are going to get output as 32 bit. These output bits are again given to the XOR for the left side bits. So we are going to see here the each operation that is performed in the round function. So coming to the first function in the round function, that is expansion of P box. So we have 32 bit as input and we need to change the 32 bit to 48 bit key. So first we need to get the 48 bits. So how we are going to expand? So these 32 bits are being expanded to this manner. That is, the last bit values are again taken as the first bits. So like this we are going to change. So you can see here the first 32 bits are remaining in the same manner, but here you are going to add the 8 bits in the first and 8 bits in the second. So here the 32nd bit is added in the first and the first bit is transposed to last. And from 4 to 28 are placed over here and from 5 to 29 are placed over here. So like this we are going to replace the values and we are going to get as a 48 bit. Then once that 48 bit are done, we are going to take the key and we are going to XOR with the output from the expansion box. So after the expansion permutation, DES uses the XOR operation on the expanded right section and the right on and the round key. Note the both the right sections and the key are the 48 bit length. Also note that the round key in the used only in the operation. So coming to the S box function. So the S boxes is said to be the confusion. So confusion is nothing but we are going to substitute the boxes. So S box can also say as a substitution boxes. So in this substitution box we are going to take the 6 bit values and we are going to get as a 4 bit as an output. So let us see how we are going to get. So we are going to take the 6 bit as an input and output as the 4 bit. So similarly we have the 48 bit. So these 48 bits are divided to 8 S boxes. So 8 6 are 48. So each box will contain 6 bits and which is converted to 4 bits. So 4 8s are 32 we are going to get as an output. So in the S box rule, so we can find here the 6 bits. So in the 6 bits, the first bit and the last bit become the row value and the middle 4 bits becomes the column value. So since we have the 2 bits for the row, so we have the 0, 1, 2 and 3 as the row values and from 0 to 15 becomes our column values. So based on this we are going to take the entry. So the output of that particular table becomes the out bit 4. So you can take and let us see the example. So the S box example. So this is the first X box. So let us take an example and see. So the input for the S box is given as 1 0 0 0 1 1. Now 1 1 becomes the row value and 0 0 0 1 becomes the column value. So 1 1 represents the value as 3 and 0 0 0 1 represent value as 1. So we have the 3 and 1. So the number value is 12 over here. So this 12 can be written as 1100. So this 110 is 0 is being replaced in the 4-bit values. So from 6 bits we are going to get the output as 4 bits. Then once the S boxes are finished, then those from the output from the S boxes, that is 32 bit, is given to the directly to the permutation table, that is P boxes. So that boxes, that is we are going to transpose the values. So the output from the S boxes, the 16th bit is being replaced in the first bit over here. The first bit is being replaced in the second bit in this box. The third bit, that is the second bit, is being replaced with the third value in this box. The 19th bit in the S box output is being replaced in the fourth place. So like that we are going to transpose in these boxes, and that output is being taken and continued, and that is being XORed with the left side bits of 32 and given to the next round. So like that we are going to do 16 rounds. So once the 16 rounds are finished, we are going to take that value as a ciphertext. So let us see the how the cipher and the reverse cipher of the first approach is performed. So initial 64-bit plain text, then we perform initial permutation, then left side bits, and we are going to take the right side bits, do the function, then XOR with the left side bits, then this is taken as the right bit for the next round, and directly the right side bits are taken for the left bits for the next round. So like that we are going to do 16 rounds. Then at the final we are going to do the final permutation, and we are going to get the ciphertext. And this is the reverse process, and we are going to get the plain text. Thank you.